we're beginning to see the very interesting application of calculus to physics. We know that for the electric field due to a point charge derived from Coulomb's law is written this way. And if we have a continuous charge arrangement like a ring of charge or a line of charge, we can cut that arrangement into small pieces, little DQs, and we can calculate the differential field element due to a small differential quantity of charge this way. And if we want to go around a ring or go along a wire or for any continuous charge arrangement, we simply add up as a vector sum or a vector integral all those contributions. Similarly, when we come to magnetic fields, there are no point charges. There are only wires carrying currents and fields produced by moving charges. And so to find the field due to a wire, say a ring of charge, a ring of current going counterclockwise around a ring, and we want to find the field at the center, we cut that wire into small pieces, and a small piece, I'm exaggerating the size, will be a ds, where s is a displacement vector. And now if we rotate, since this is a three-dimensional problem, we rotate this ring so it's tilted to the side, where the current at the top is now coming out of the page, going down on the outside, then returning into the page or the screen at the bottom, and then heading up on the back of the screen in that way. And then we can find the magnetic field at a point along an axis perpendicular to the face of the loop. Any distance we choose, A, along this x-axis. And for reference, we'll consider this direction x, this direction y, and into and out of the screen, z. So, to do this, we use the Biot-Savart Law, which says that the small contribution, the differential contribution to a magnetic field due to a small differential length of wire will look like this. Mu naught, the current, the cross product of the ds vector with a unit vector r hat, which is a unit vector, directional vector that points from the ds toward the point considered. So in the first diagram, this would be that vector points from the ds directly to the r hat. And you can see that the r hat, this is our r hat, a unit vector pointing from the ds, is perpendicular to the ds. And if you do that cross product using right-hand rule number 3, you cross the ds into the r hat and your thumb points out of the board. That indicates that the direction of the magnetic field at the center is, according to our diagram, in the positive k hat direction coming out of the paper. If we go to the second diagram where we're finding the field at point A, the r hat, I'm going to exaggerate the length of it, would be in that direction. And the ds is coming straight out at us. And if you draw the line from r hat pointing down to A, the cross product of ds coming along the z-axis cross with the r hat vector has to be perpendicular to both. So the dB, the direction of dB, is going to be in that direction. And that forms an angle theta with the x-axis. And skipping the trig, that is our r, the radius of the circle, and in this diagram this is the same angle theta. You can do the trig to prove that to yourself. And if we go to the bottom of the page, where the x is, we have a ds going into the screen. We have an r hat that points towards A. And so we do ds cross r hat. The dB for that one has to be perpendicular to the r hat vector. It'll be the same length. It'll be the same angle theta below the x-axis. So this is dB for the ds at the bottom. And this is dB for the ds at the top, if you can keep straight all those terms. And if you can picture what's happening, you see that for every ds, I go around this loop, cutting it up into ds's. Each one is going to give me a dB, and if I looked at all of those dBs, they would sweep out a cone of angle theta around the x-axis. And so to calculate the total field B due to this ring at point A, we need to integrate all the dBx's. And so that means we integrate the expression above, which, looking back, I never finished. Any dB is going to be that divided by, this is Biot-Savart Law, 4 pi, times r squared, where r is the distance from the ds to the point. So in this problem we just left, we're going to add all the dBx's. So any dB is mu naught I. The ds cross r hat, it's hard to convince you in 2 dimensions, but the ds and the r hat for all these situations are perpendicular to each other. Recalling the cross product, ds cross r hat means the magnitude of ds times the magnitude of r hat, which is 1, a unit vector, times the sine of the angle, in this case 90 degrees. So the ds cross r hat reduces to just ds. And that needs to be divided by 4 pi, the distance from the ds to the point A. Can you see what that is? Let me draw that triangle for you. It's this distance here. If we look at our angle theta, and there's the x-axis. So this is a right triangle. One side is r, the other side is A. This is r squared plus A squared, square root squared, so it's just that. That's the distance squared. Now remember, we're pulling out the x component, so that's going to be the cosine of theta. If we look to theta of our triangle, we can see that cosine is the adjacent, r, the radius of the circle, over the hypotenuse, the r squared plus a squared square root. So the cosine of theta, check this out, is r over r squared plus a squared to the 1/2 power. Okay, so that's our dBx. We're going to integrate all of those, and our total B at this point A, remember what we're doing, equals the integral of all the dBx's. So the B is the Bx. We already said that. All the yz components cancel in pairs. Only the Bx's survive. And so we're doing the integral. Now notice all the terms inside the integral, every one of them except the ds is a constant. The mu naught is a constant. The I is a constant. The r, radius of the circle, is a constant. The a for this problem is fixed. We can vary it to another problem, but in this problem we've chosen an a. And so everything except the ds comes out. We have mu naught I. Whoops, I don't want the ds there. Let me erase that. Mu naught IR all comes out over 4 pi. I'm going to try and condense this into r squared plus a squared to the 3/2. All times the integral, the only thing left is the integral around the circle of ds. If we add all the ds's around a circle, what do we get? We get the circumference of a circle. And so that's 2 pi r. So the 2 pi can cancel the 4 pi, leaving a 2. And pulling all the terms together, we get that our answer, the magnetic field at a point A, due to a single current carrying loop of radius r, is going to be mu naught I, the current in the loop, r squared, the radius of the circle, all divided by 2 times r squared plus a squared to the 3/2 power.